What is the thing that makes it basic or important? Because again, we agree that there are numerous questions you can ask. Is it the fact that you need a new method to solve it, or you discover, well, it's only with hindsight, only after it's solved, you know that it was a good question, or you can tell in advance?
There are some questions like the sunflower. It is absolutely interesting on its own, right?
Can you explain it?
Yes, somewhat, yes. So we have n-element sets, and then what we are interested, then how big how many sets we have to have, so that there we always will find 3 of them, so that their pairwise intersection is the same. So it looks like a sunflower. That is why it is called the sunflower problem.
So
that the intersection is the middle of the sunflower, and then these 3 ear patterns are disjoint.
I completely agree. It's a very interesting problem. I tried it myself, but probably not close to the amount you put into it.
That was the first problem really what I wanted to solve when I was university student. I heard it from Paul before we started to work on these elementary number theory problems, and this was my favorite problem. Yes, I put at that time a lot of time, and I am planning to put even more time in it. Also, I am well aware then the probability that I can solve it is very little, and even to make a significant progress, because most probably it is just not something that you just can attack with brute force and then this or that simple idea. It should be deep. Most of the combinatorists worked on it at some period of their mathematical career.
So it's a really interesting test case, I think, for me to probe what makes a problem interesting. Of course, you could state it in one sentence. We know that the size of such a family has to be at least, if these are n-element sets, and it has to be at least something like 2 to the n. We know that if we have n to the n, then it's enough. And these are all simple arguments. And so the question is, what is the truth in the middle? It doesn't look like such a big gap. But, for a bystander, a bystander mathematician would wonder why should you or any other combinatorialist invest years in trying to figure out this particular one as opposed to,
You don't give an answer to the bystander. Yes, that is the right solution. Yeah. It's just clear. Really, nothing more can be said, because we don't know whether the solution will... It's a beautiful problem. If you look at the picture, yes, you go to the museum, yes, you feel that this painting is beautiful, yes, and this problem is beautiful. So there is such a notion as beauty most probably in mathematics, which is an important part of mathematics. Without it, mathematics would be, at least by my opinion, is much, much poorer. Mm-hmm. So definitely for me, this is a beautiful problem. And most probably, but that we of course cannot say with certainty, will require methods which will move combinatorics and some part of combinatorics and will be applied in many other areas. I just cannot imagine that without methods you can attack this problem. So maybe actually this will not be a problem in discrete mathematics, but maybe we need, yes, continuous mathematics and different branch of mathematics. At least we have to adapt either the technique or the results themselves. I don't know, I am just guessing. Mm-hmm. I have a plan to work on it again. Look, that is one advantage, not too many advantages are to be old, but that is one, then without any risks you can not produce anything. Especially in US, they don't fire you, yes, they just cannot fire you if you are over 70. So
this problem, of course, this feeling that it's beautiful and basic was vindicated long ago, because it even the weak bounds we know were used in lots of areas. In fact, just a number of computer science papers in which it is used to a really important effect, mainly the upper bound, is numerous, and it comes in matrix multiplication. It comes in pseudo-random generators.